let's start. So one of the things we were asked, one of the questions we were asked to answer in our talks is how ITAMP shaped our careers. And I decided for myself, wow, I'm getting something that I always wanted to have, which is that. So one of the papers I published during my ITAMP postdoc years was a paper on the confined scattering. So there were two things there. So one is the modification of the scattering properties of two atoms in a waveguide. Another thing was an introduction for giving him a way to generate an atomic Tong-Girardot gas in a laboratory. And so since then it had, well, more than 800 citations and counting, and actually probably in 4 or 5 years I'll have 1,000 and I'll have a large party. So that's the plan. And this work was directly inspired by 3 particular theses in Rick Heller's group. So that was Adam Lupu-Sachs, Jesse Hirsch, and Alex Barnett. And since then, Rick was constantly encouraging me to continue on confined scattering, on the generalized theory of scattering. So abstracting myself from actual particles, but thinking in terms of Lippmann-Schwinger equations and discovering and rediscovering new things. So since then, the effects predicted in this paper were observed experimentally. So so the confined induced resonance, a particular resonance in confined scattering was seen, and the bound states that are highly non-one-dimensional. So that include all orders in the Born scattering. So they were observed experimentally in Tillman-Esslinger's group. And
1,000 citations.
What?
Do they also have 1,000 citations?
Lots of. I mean, those are more recent, but yes, some. I'm not 1,000 yet. So on Google Scholar, it's much more than 1,000. But Web of Science is more serious. So, and as I said, it also linked the confined scattering to impenetrable bosons, and impenetrable bosons. Since then, they shape. They are actually the model that we work a lot with, and in the main part of my talk, you will again see impenetrable bosons, but with a different mass. So then I moved to the University of Southern California. So as I said, most of ITAMP postdocs, they land the job right away. So I landed the job right away. I got my tenure in 5 years there. So also, I mean, thanks to ITAMP. And in fact, while there, I was, for the first time in my life, I got in my hands the so-called purple book. So that's Bogolubov is Ergin Korepin on the quantum inverse scattering method. So I found the thing which was called a representative state hypothesis, and it inspired our work later published in Nature on the actual microscopic origins of thermal lisibility in quantum systems. And the idea was that the only way how quantum system, which is a linear system, can produce irreversible predictions is to shrink the quantum expectation values of observables in different quantum states to a single line. And this is a hypothesis expressed by Mark Srednitsky 10 years before us, and we gave an unambiguous numerical justification for that. And so it was featured in the New Scientist. So they had a paper about some artists who do exploding balloons with milk and make pictures of those, but also in the same article there was a quantum balloon because one of the systems we studied was a box for two-dimensional atoms that suddenly opens, and we studied thermalization there, and so they were mentioned that as researchers who research hypothetical atom scale quantum balloons. And now I'm here. So since 2007, I'm at UMass Boston. So that's us. Our students get boats for free from 9 to 5, so they can have lunch breaks on boats. And actually, my impression is that sometimes it takes longer than a lunch. Yes, and it's a beautiful place to be. So one of the things, so before I go to the main talk, so one of the things I did there was I assembled all simple qualitative methods I know to actually cover problems in many body theory, in cold gases, in elementary quantum mechanics, and also in integrable PDEs. And so the longest problem in the book is about the so-called impossible potentials. And it is heavily based on a paper published by Brian Granger, who was ITAMP postdoc, and Dorothy Bloom, who's a very frequent, probably every year visitor at ITAMP. So it was the whole it was heavily inspired by that. So our projects for the last 15 years, they allow a placement on a two-dimensional plane with a two-dimensional metric. So on the horizontal line is between integrable and ergodic, and vertical between quantum and classical. So hardcore bosons we already know. So we later on we started thinking about relaxation in integrable systems, and so what we discovered was the so-called generalized Gibbs ensemble. So if you look, this is a momentum distribution of hardcore bosons. So initial momentum distribution has 3 peaks. In the beginning, it thought it is ergodic. So it tried to broaden the peaks, but then they stopped. And the reason why the relaxations, I can show it again. So the reason why, so that's the initial momentum distribution, and now so it starts evolving, it broadens, but then it stops. And the reason why it stops, it's the high integrals of motion present in hardcore bosons, and we managed to generate a theory which is inspired by normal thermodynamics that takes into account the high integrals of motion. So this transition you already saw. So that's the eigenstate stabilization hypothesis. So we worked. We worked on two-dimensional billiards. We worked on high conservation laws in one-dimensional systems, in particular conservation of the chemical decomposition. So the upper line is classical. So this is the classical field theory in an attempt to treat 1D Bose-Hubbard model in the same terms as Fermi-Pastor-Ulam. So this is the most esoteric part, probably the relationship between integral partial differential equations and quantum mechanical supersymmetry, and it was esoteric enough to warrant an invited talk at the American Mathematical Society meeting, and I'm pretty proud about it. And so, and one of the so in the middle, so it's a particular symmetry, dynamical symmetry we have in a two-dimensional Bose gas that leads to the absence of damping and amplitude induced shift of the frequency of the monopole modes, and and this is a work in a tight collaboration with an experimental group in Paris Nord, group led by Hélène Perrin. So this project is on utilizing non-trivial integrals of motion in integrable PDEs for useful purposes, and in particular we wanted to know if we can use high conservation laws to stabilize interferometry with strongly interacting objects like Groth-Petoevsky solitons. And in particular, it turns out that if instead of doing interferometry with solitons, you do it with what's called breathers, you can the splitting becomes highly controlled due to the high conservation laws. And in particular, if you shoot a breather, and this is a breather, on a barrier, regardless of the initial conditions, it always splits into 2 parts. One part of a size 1, another part of a size 3, and this is a consequence of high conservation laws. And so this way we are hoping to beat a strong dephasing that would come otherwise from the imperfect beam splitting. So remember, those are strongly interacting. So if you have a disparity of 51-49% in a beam splitting, it will, this phase, due to interactions, it will accumulate and it will destroy the interference. So, and today we are here. So where is that? So today we are here. So it's about little known instances, actually previously unknown instances of integrability in one-dimensional gases, and how it may affect relaxation in two-mass mixtures of cold gases. So, right. So the plan for the main presentation is that we will talk about integrability in three bodies, three different mass mixtures of one-dimensional hardcore particles. So we'll discover a prominent manifestation of integrability as a new instance of a Newton's cradle. So in particular, you can build a Newton's cradle not only with masses 1, 1, 1, but also with 1 square root of 5 plus 2 square root of 5 plus 2. So the result will be the same. Heavy particles will exchange their velocities, and the middle one will keep its velocity. And we'll see that at the many body level, we'll see the slowdown of relaxation at magic mass ratios, and we're hoping to that it could be seen experimentally, where you control not the real mass but the effective mass in optical lattices, and then an experimental group like the one Dominic Schneble is running in Stony Brook, it might be ready for that. So their mass control is within a factor of 40. So let's see. So it is all related to the so-called root systems. And if you ask me a question, I'll tell you what the root systems are. They're one of the most simplest and most beautiful and most powerful objects in modern mathematics. But all we need to know at the moment is that they're used to classify kaleidoscopes. And the most compact definition of a kaleidoscope I found I invented is a kaleidoscope is a system of mirrors where the seams between the mirrors are seamless. So this is an example of a kaleidoscope of a human-sized kaleidoscope in San Francisco in the Exploratorium. So you're standing in between three mirrors, 60 degrees between them. So I believe that's the origin. So it's hard to tell, but I think that's the origin. And those are two reflections. And if you look at the shoulder, so shoulder continues without interruption. So if you really clean the seam, you wouldn't know where the contact between the two mirrors is. And it turns out that there are only, in fact, if you count them, there are only 8 or 9 types of kaleidoscopes in the world. So some of them run in all spatial dimensions, but most of them they exist in some particular dimensions. And it turns out that there is an overlap, intersection, which is narrow but non-zero intersection between kaleidoscopes and beta ansatzable many-body systems and exactly solvable many-body systems. So. And as I said, I mean, all these phenomena, so quantum billiards, integrable many-body systems, root systems, kaleidoscopes, they're all related, and I would need probably series of three talks to tell you how they are related. So the history of the subject is that in 1960, Marvin Girardot discovered the Thomson-Girardot model. Which is a realization of a particular root system which is called n minus 1 for n hardcore bosons. In 63, Lieb Lineager presented a finite strength interaction realization of this root system. It was a great development because finite strength interactions are more physical. So and then Maguire and later Gadan they proved that there are only a few. There are only few exactly solvable models with delta interactions, and to this extent, so this generated my early childhood trauma because Gadan in his book he says that We will not discuss the exceptional root systems, not to speak about real pariahs, non-crystallographic root systems, because they don't lead to any interesting pairwise interacting particles. And I was since then I was thinking, and I knew this book. Actually, I knew this book in Russian translation, and it is recently, a year ago, it was translated to English. And so in this presentation, we'll try to return back to the 60s. We imagine ourselves in the 60s, and we return back to the hard cores, forgotten, and see if the giants overlooked something there. And so let's look at a particular root system Godin named uninteresting for physics, and that's an exceptional root system G2. Formed by, so this is, in short, root systems are sets of vectors with particular properties, and this is this root system. So you can build an exactly solvable quantum billiard with with these angles between the mirrors. You can put any kinds of boundary conditions between them. So any relationship between the gradient of the wave function and the value of the wave function on the boundary. So you can start changing the boundary conditions, and then when you pass to hard walls, it turns out that this very system describes the relative motion of particles of mass 1, 3 and hard wall on a ring, and this is one instance where I mean those are real particles. So again, it's a hard wall, ring, and mass 1, 1 and 3. So now we pass to the so-called non-crystallographic root systems, which are not interesting in mathematics at all. I mean, they don't classify anything, but for us, they still give solutions for wedges. So not closed billiards, but wedges. So we can also play with the boundary conditions. And then it turns out that for hard cores, for infinite walls, what we realize is 3 particles, not on a ring, on a line, with masses square root of 5 plus 2, 1 square root of 5 plus 2. And it's, so up to date, this is a table that includes everything that was both mentioned and overlooked by the giants. So this is an example I just gave. So there's the whole families of integrable systems on a line with 3 different masses, and so this was mentioned in the 60s, and this one was so this corresponds to the Lieb-Lininger model, and this corresponds to a Lieb-Lininger model between 2 walls. So that's root system B, which is in this case coincides with C. What's interesting is that we can go even further. There is a prominent, very visual manifestation of integrability, especially for the odd for the angles between the 2 mirrors, which is pi over n, where n is odd. Namely, there is a little known generalization of the notion of a Newton's cradle. So let's take 3 particles, square root of 5 plus 2, 1 square root of 5 plus 2. Imagine so they come together from they come from infinity, they collide, and as a result of a 3-body collision, left heavy particle exchanges the velocity with the right heavy particle, and the middle light particle retains its velocity. And now an interesting question arises. So all that, formally speaking, doesn't allow any generalization to high numbers of particles. It's all a 3-body effect. But what if nevertheless we have a mass mixture with this particular mass ratio, and what if 3 particles every so often there are 3 particles that come together close enough to undergo a whole 3-body collision as if they didn't have any neighbors. So what will happen in this case is that they will collide. Will spend in this case we'll spend the whole 5 collisions. So green is heavy, purple is heavy, blue is light. So they come together. so light particle bounces. It retains its own velocity. Green exchanges the velocity with purple. Purple exchanges velocity with green. We look at the momentum distribution. We wasted the whole 5 collisions without increasing entropy. So, which will indicate that maybe we can see some slowdown in relaxation in this case. So this is another example just to show you that it can happen for any set of velocities, not necessarily middle velocity being strictly horizontal. So again, so light green comes, which is light, so collides with yellow and blue, and then by the end of the day, I mean, if you look at it, it seems so. If you look at it at this scale, you would think they don't interact. And so what we do now is that we run, well, in this case, classical simulation with 200 heavy and 100 light particles. Initial distribution is that so light particles are at rest and the heavy particles are beam split. Half of them moves with the velocity +1 to the left, and half of them moves with the velocity +1 to the right. So it's a nice zero parametric model. I mean, there's no parameters in it. So what we look at is the following observable. So it's a ratio between the mean of a particle's square of the kinetic energy divided by the square of the mean. So A, in the thermal equilibrium, we would expect equipartition of energy. And if in the end all of them reach maximal distribution, so this particular observable must be equal to 3. And what we see is that for all mass ratios we studied, we didn't go to the equal masses, but we didn't see an actual transition to the equal masses. So we suspect that it remains ergodic all the way to the exactly equal masses, but we didn't study it well. But as you can see that for this range of masses, the motion is perfectly ergodic. So it reaches exactly 3, which is predicted by the thermal equilibrium. Which makes it nice because usually, and this is a technical but very annoying difficulty. So usually, the systems you study, they're in between integrable and ergodic. And when something doesn't thermalize, you don't know if it really doesn't thermalize even at infinite time. It's just stuck there, or you didn't propagate well. You didn't propagate for a time long enough. So in this case, we know for sure that it thermalizes to the prediction of the thermal equilibrium, and all we need to study is the relaxation time. And what we discover is that exactly at the kaleidoscopic mass ratios, at the mass ratios where the three-body triplets constitute integrable systems, we see peaks in the relaxation time. Well, peaks are not super enormous because the process that is sensitive to integrability is pretty rare. Again, you have to have 3 particles that come close enough together that undergo a full 3-body collision as if they had the whole space available, but the effect is definitely there. And so as I said, so we are looking for an optical lattice realization of the effect, and we'll start soon quantum simulations and so on and so forth. But it's definitely at least at the classical level. I mean, the effect is pretty prominent. So a philosophical question that one can raise, because now it is so. Many things are distinct from the standard Lieb-Lininger model with equal masses. Is that what is the real primary cause for these peaks? So one cause could be the actual integrability, the ability to write the solution, the actual wave function. But what one realizes is that in this for 3 hard cores, one can always write down an exact solution. It's very easy. Integrable, bet ansatz or not. Is it the Young-Baxter property, the fact that the outcome of the 3-body collision doesn't depend on the order of the 2-body collisions in the cascade, or is it really the Newton's cradle, the fact that the velocity distribution remains invariant on this 3-body collision? And my bet is it's C, because even for B, the thing is that when we have three bodies, but when you watch the one body observables, so all this three body motion gets projected to a single plane, and I'm not sure if it's enough for humans to recognize something peculiar about the motion. But Newton's cradle is unambiguous. You you have a process where you look at the one body energy distribution, and it simply doesn't change. But this is a question for the future research. So as a summary of the main part, so we looked at the non-crystallographic and exceptional root systems, and we found some previously unknown examples of integrable quantum and classical systems. So we found so we found an extension of Newton's cradle, and when we embed these triplets into an actual many-body system, we do see peaks at the integral mass ratios, and we're hoping to see an actual optical lattice realization where the actual masses are replaced by the optical lattices. So the work, all what was happening with integrability and thermalizability. So I was collaborating with many people, as you can see. So and Rick Heller was always very encouraging about this, and I'm grateful to him for that. And well, that's the support, and thank you very much.
All right, we have plenty of time for questions.
I thought it was 30 minutes including questions.
It was 35 actually. But that's
Okay. Yeah.
So how are you going to get the mass ratio when to the square root of 5 plus?
Effective mass. So you
use the lattice to change.
Yeah, you use the lattice to change the effective mass. You use very low densities, and at low densities, particles behave. I mean, you can't forget about the lattice.
But there still has to be a one-dimensional tube.
Yes. Yeah. It's a one-dimensional. Yeah, it's a one-dimensional motion along, and the lattice along it. There was an interesting. I mean, there's an interesting experimental work. There's a group in Canada, in Toronto. So they study how well the effective mass shows up when you put a single atom in an external field, and it turns out. Huh? I think so. Yeah. So it turns out that in the beginning, atoms behave as if they had a real mass, but then there's the average over oscillations, and then they accelerate according to the effective mass. And so in collisions, I think the very same thing will happen. So at the very first instance, they collide as normal atoms, but then as they start tunneling. Yeah.
So you looked at all boundary conditions in the pictures you showed us. And that was a 12-sided?
In particular, the 12-sided, yes.
I was just wondering, what's the relationship if you use 6 sides between 6 sides with all boundary conditions and graphene, which basically, if you do band structure theory, you don't have any, you have periodic boundary conditions, which I think translates into many different boundaries. I don't know if there's a one-to-one mapping between condensed matter boundary conditions, so to speak, and these boundary conditions.
It's periodic. Well, they're all actually they're all periodic, but but you may or may not have a jump at the actual boundary. So what the thing control, what they have here is a delta function with a strength 1. So but then once applied this boundary condition, you require periodicity.
But you have a continuously variable psi over psi prime, or psi prime over psi boundary condition, right?
Yeah.
And
At the boundary.
you could have done band structure theory, right? You could have slowly varied it, and then
Yeah, and that's
the energy of the state, right?
And that's yeah, and that's exactly how you in the end. That's exactly what beta-ansatz boils to. I mean, you compute the band structures. So indeed, I mean, in the very end, it is yeah, it's exactly that.
So I have a very simple question. So when you want to do this experimentally, what would be the actual time scales that you need to observe the experiment, especially since you are looking for something where the relaxation time could be quite
Yeah. So the peaks you see at between 3 and 6 collisions per particle.
Okay,
So which is yeah. I mean, of course, I mean in the lattice motion is slow and so forth, but it's a few collisions per particle. So it is yeah, it is your analog of the magic 2.7. So it's three-dimensional gas of hard spheres thermalizes in 2.7 collisions. So in 1D it's 2.7 is more like 6.
Of these models, integral models, you found that were this. Yeah. So some of the models contain hardware. Yeah.
Actually, all of them. No, many of them. Yes, yeah,
Many of them.
yeah.
So this hardware is directory boundary condition. So do you have any integral models with Newman boundary condition? That means
Okay, so billiards are integrable for any boundary condition, both Newman, Dirichlet, and in between.
oh,
Billiards are, but only if you there are only rare billiards that map to 3 particles, and the geometric reason is okay. So the geometric reason for that is that so for 3 particles, you have a space tiled by triangles formed by 3 sets of parallel lines. Okay, so that. So one set, another set, another set. So integral billiards are generated by tiling of a plane by triangles that tile the plane by flipping with respect to their sides, and there are only a few intersections. So whenever you have an intersection between, generally speaking, between tiling the space by simplexes that are flipped, that are reflected about their sides, and tiling the space by simplexes which are formed by n sets of parallel lines, you have an integrable, you have a beta-ansatzable many-body system, but there are only a few of them. But answering your original question, so if you're only interested in triangle billiards, then it's any boundary condition. And actually, there's many more integrable billiards than that. I mean, there's one very specific in 4 dimensions, the so-called F4. I mean, there are 3 very exotic in 6, 7, and 8. But so far, I don't think any of them have anything to do with actual particles. They're really billiards with walls and the wave equation inside.
One last question.
I guess I just maybe I could comment on my own question. It just occurred to me that, of course, if you send a wave packet, let's say, at a wall, a straight wall, with any one of your boundary conditions, it will reflect.
Right.
Neumann boundary conditions cause reflection. Of course, the wave function isn't 0 at the wall, but it still reflects.
It will.
And 100%, nothing gets through. And likewise, everybody knows Dirichlet reflects. But any strict boundary condition will cause 100% reflection.
Really? No. In between you have a delta function. Oh, no. A delta function partially transmits, partially reflects. No, wave packet, part of it will go through, part of it will reflect. So these intermediate boundary conditions, they're just a delta function of a finite strength. That's it. So infinity is a hard wall.
The delta function of finite strength will not impose an energy-independent boundary condition.
So maybe we can discuss this afterwards.
Yeah, I'll think about it. Yeah.
Thanks again.
Thank you.